The universe is a vast, mysterious place, filled with wonders that defy our understanding and challenge everything we think we know about the cosmos. Just when we believe we've unraveled some of its deepest secrets, it throws another curveball our way, something so bizarre, so unexpected, that it leaves even the most seasoned astronomers scratching their heads. And few cosmic phenomena embody this mystery better than the mind-bending reality of duodecuple star systems. Yes, you heard that right, not just 2 or 3 stars orbiting each other, but 12. 12 suns locked in an intricate gravitational dance, weaving through space in patterns so complex they seem almost impossible. Imagine standing on a planet in one of these systems, looking up at a sky where 12 suns rise and set in a chaotic, mesmerizing ballet. Some might blaze side by side while others drift in distant orbits, their light flickering like celestial fireflies. The sheer scale of such a system is staggering, a cosmic puzzle that pushes the limits of physics and human imagination. But here's the thing, these systems aren't just rare. They're laboratories of the bizarre where the usual rules of astronomy seem to break down. Strange gravitational quirks, unexplained energy fluctuations, even hints of planets somehow surviving in this stellar maelstrom. Each discovery raises more questions than answers. What makes these 12 star systems so baffling? How do they even form in the first place? And what secrets might they hold about the universe's most fundamental laws? Strap in, because we're about to dive into 30 of the strangest, most jaw-dropping discoveries ever made about duodecuple star systems. From rogue stars behaving unpredictably to eerie signals that suggest something even more mysterious lurking in the shadows, this journey will take you to the edge of cosmic understanding. One thing's for sure, by the end, you'll never look at the night sky the same way again. The first recorded duodecuple star system shattered everything astronomers thought they knew about stellar formations. It wasn't just that 12 stars could exist in a single system, it was the sheer improbability of such a delicate balance surviving the chaos of space. The discovery happened almost by accident, buried in data from a sky survey designed to map binary and triple star systems. Scientists were sifting through faint light curves when they noticed something bizarre. A set of 12 stars whose gravitational pull on one another created patterns so intricate they defied all existing models. At first, researchers dismissed it as an error, a glitch in the telescope's software, or a rare alignment of unrelated stars. But as more observations piled up, the truth became undeniable. Nature had built something far stranger than anyone predicted. The key to unraveling this cosmic puzzle lay in the technology that made it visible. Advanced spectrographs capable of splitting starlight into razor-thin wavelengths revealed subtle Doppler shifts, tiny hints of motion that betrayed the presence of multiple stars tugging at one another. Meanwhile, high-resolution imaging exposed faint companions hidden in the glare of brighter stars, like finding needles in a haystack of cosmic fire. Even then, the system's stability seemed impossible. Conventional wisdom said such a crowded stellar neighborhood should collapse into chaos, with stars either merging or flinging each other into the void. Yet here they were, locked in an orbital waltz that had somehow lasted billions of years. What made this discovery even more astonishing was the realization that duodecuple systems might not be as rare as we once thought. Hidden in the noise of older observations, astronomers began spotting clues, odd fluctuations in brightness, unexplained gravitational wobbles, that hinted at more of these celestial oddities waiting to be found. Suddenly, the universe seemed to be whispering a secret. Its rules were far more flexible, far more creative than we'd ever imagined. And if 12 stars could dance together against all odds, what else might be out there, lurking just beyond the edge of our understanding? One of the most bewildering aspects of duodecuple star systems is the gravitational anarchy unfolding among their 12 stellar members. Picture a crowded dance floor where 12 partners, each with their own rhythm and speed, keep changing moves without warning, now pulling closer, now spinning away, their movements erratically out of sync. That's the kind of chaos these stars create on a cosmic scale. Traditional celestial mechanics, which neatly predict the orbits of binary or even triple star systems, completely fall apart here. With 12 massive objects tugging at one another, their paths become a tangled web of unstable loops, sudden pivots, and near misses that supercomputers struggle to simulate. Take one particularly volatile system where 3 tight pairs of stars orbit a central quartet, while 5 outliers weave unpredictable figure eights around the group. Observers tracked these stars for years, expecting their orbits to stabilize into some semblance of order. Instead, the stars seemed almost alive, jostling for position, stealing momentum from one another, and occasionally flinging a companion star into a wildly different trajectory. Simulations showed that even minuscule changes, like a slight nudge from a passing gas cloud, could send the entire system spiraling into a new configuration within just a few centuries. What makes this turbulence so fascinating is how it defies long-held assumptions. Astronomers once believed multi-star systems would naturally eject excess members until only a stable few remained. Yet here, against all odds, a dozen stars persist in their chaotic ballet. Some theorists suggest hidden forces might be at play, perhaps dark matter subtly anchoring the system, or undiscovered planets acting as gravitational mediators. Others speculate that we're witnessing a fleeting moment in cosmic time, a rare alignment destined to collapse, but when, 1,000 years from now? A million. The unpredictability is both thrilling and humbling, a reminder that the universe delights in breaking our models, and yet amid the pandemonium, there are fleeting moments of eerie synchronicity. In one recorded instance, 6 of the 12 stars aligned briefly in a near-perfect hexagon, their gravity temporarily harmonizing before scattering again like marbles on a vibrating plate. These transient patterns hint at layers of complexity we're only beginning to perceive, where chaos and order aren't opposites, but partners in an endless cosmic dance. If you thought 12 star systems were chaotic just for the stars themselves, wait until you hear what happens to any planets brave or foolish enough to form in these gravitational war zones. Imagine a world where the ground beneath your feet is at the mercy of 12 different suns, each yanking at it with competing tides of gravity. One moment, your planet might be drifting peacefully in a stable orbit. The next, a passing star's gravitational kick sends it spiraling into a new, elliptical path, or worse, hurls it entirely out of the system into the freezing abyss of interstellar space. These aren't just theoretical nightmares. Observations of duodecuple systems have revealed planets caught in a perpetual tug of war, their orbits stretching and compressing like rubber bands. In one case, astronomers found a gas giant locked in a bizarre figure 8 trajectory, looping around 2 different pairs of stars before slingshotting past a third. The forces at play here are so extreme that the planet's atmosphere is literally being pulled apart, leaving a glowing trail of ionized gas in its wake like a cosmic breadcrumb trail. But here's the real shocker: some planets somehow survive. Take the hypothetical world of a rocky planet nestled snugly in the habitable zone of one star, while the other 11 blaze in the distance. At first glance, it seems impossible, until you realize the star's chaotic motions might actually cancel each other out over time, creating temporary pockets of stability. Picture a marble rolling around a spinning plate. If the plate wobbles just right, the marble stays put. These fleeting sanctuaries could, in theory, allow a planet to cling to life for billions of years, basking in the glow of multiple suns while weathering occasional gravitational storms. The implications are staggering. If life could arise in such a volatile environment, it would have to be unshakably resilient, evolving under skies where the suns shift positions over centuries, where seasons change unpredictably, and where the very length of a day might stretch or shrink as tides flex the planet's crust. It's a survival story written in gravity and fire, proving once again that the universe thrives on defying our expectations. And if planets can endure this stellar madness, what other impossibilities might be waiting in the cosmos's most chaotic corners? With so many stars crammed into a relatively tight space, duodecuple systems become cosmic demolition derbies where stellar collisions aren't just possible, they're practically inevitable. Normally, stars maintain a polite distance, orbiting each other with vast stretches of emptiness between them, but pack 12 massive bodies into the gravitational equivalent of a crowded elevator, and all bets are off. The slightest orbital miscalculation, the tiniest nudge from a passing star, can send two suns careening toward each other at terrifying speeds. When these collisions happen, they create some of the most spectacular fireworks in the universe. Take blue straggler stars that should have aged into red giants billions of years ago, but instead burn unnaturally young and hot. In duodecuple systems, they form when two smaller stars slam together, merging their fuel and resetting their cosmic clocks. The result is a monstrously bright star that defies stellar evolution, shining like a rebellious teenager in a retirement home. But collisions don't always end in mergers. Sometimes the sheer force of impact flings stars away at unbelievable velocities, creating what astronomers call hypervelocity stars. These rogue projectiles blast through space fast enough to escape their galaxy entirely, leaving behind a telltale streak of shocked gas and radiation. In one observed case, a hypervelocity star rocketed outward at over 1 million miles per hour, so fast it crossed the distance from Earth to the Moon in less than 15 minutes. What makes duodecuple systems so uniquely violent is the chain reaction potential. A single collision can destabilize neighboring orbits, triggering a cascade of near misses and secondary impacts. Computer models show these systems might experience major collisions every few 100,000 years, a blink of an eye in cosmic terms. And with each crash, the system reinvents itself, stars reshuffling like a deck of cards thrown into a hurricane. Yet amid this chaos lies a silver lining for astronomers. These violent encounters act like natural laboratories, letting us witness rare stellar phenomena that would otherwise take billions of years to unfold. Every collision peels back another layer of mystery, revealing how stars live, die, and occasionally cheat death by crashing into their neighbors. It's a reminder that even in the most crowded corners of the cosmos, there's always room for surprise, and that sometimes destruction paves the way for discovery. Among all the bizarre phenomena tied to duodecuple star systems, nothing has set astronomers' hearts racing quite like the unexplained radio signals crackling from these crowded cosmic neighborhoods. These aren't your ordinary stellar radio waves, predictable, steady hums from stellar winds or magnetospheric activity. These signals pulse and stagger in erratic patterns, sometimes vanishing for decades before reappearing with renewed intensity, as if the universe itself is playing an interstellar game of Morse code. When first detected, they were dismissed as interference, maybe a glitch from a passing satellite or an echo from Earth's own radio noise. But as more of these signals emerged from multiple 12-star systems across the galaxy, the astronomical community had to face a startling possibility. Something entirely unknown was at work. The signals defy easy classification. Some repeat at irregular intervals like a cosmic drummer losing the beat, while others blast a single, powerful chirp before falling silent forever. One particularly infamous emission, dubbed the 12-star whale, lasted 72 seconds, an agonizingly slow crescendo of frequencies that swept upward before cutting off abruptly. Attempts to explain these bursts using known physics have hit dead ends. Could they be the result of tangled magnetic fields, stretched to breaking point by the system's chaotic gravity, or perhaps shock waves from near-miss stellar collisions rippling through clouds of ionized gas? The leading natural theory suggests they're caused by gravitational lensing storms, where the combined pull of 12 stars bends passing radio waves into distorted, amplified bursts. But even this fails to account for the signal's eerie structure, some of which bear uncomfortable resemblances to artificial patterns. This is where the debate catches fire. A fringe but growing contingent of researchers points to the signal's unnatural-seeming repetition rates and spectral fingerprints, arguing they might be technosignatures, leaks from some unfathomable alien technology. Imagine a civilization advanced enough to harness the energy of multiple stars, perhaps using their gravity as a slingshot for interstellar travel or even manipulating space-time itself. The idea isn't entirely far-fetched. After all, in a system with 12 suns, the raw energy available would dwarf anything a single star could provide. But mainstream scientists urge caution, noting that the universe has fooled us before with natural phenomena that mimicked intelligence. Remember pulsars. Their clock-like pulses were initially mistaken for alien beacons until their true nature as spinning neutron stars was uncovered. What makes these signals especially tantalizing is their sheer persistence. Unlike fleeting cosmic anomalies, they've been detected across multiple decades, suggesting whatever produces them isn't just a one-off fluke, it's an ongoing process. Recent advances in radio telescope arrays have finally given astronomers the tools to triangulate their origins with precision. Early results pinpoint the emissions not from any single star, but from the turbulent gaps between them, where gravitational forces churn space into a froth of plasma and twisted magnetic fields. Whether natural or something far stranger, one thing's certain: these signals are rewriting the playbook on what we thought was possible in even the most extreme corners of the cosmos. And with every new detection, the mystery only deepens. Trying to measure the light from a Duodecuple star system is like staring into a disco ball spinning at warp speed. Just when you think you've pinned down one flash, a dozen others flare up to throw you off. Early astronomers studying these systems hit a wall when their instruments recorded wild, nonsensical brightness swings. One night, a star might appear calm and steady. The next, it could flicker like a candle in a hurricane before vanishing entirely for weeks. At first, observers blamed faulty equipment or cosmic dust clouds passing through the line of sight. But as data accumulated, an unsettling truth emerged: the light variations weren't errors. They were the system's brutal reality. The chaos stems from a celestial game of peekaboo played with 12 stellar participants. As the stars orbit, they constantly eclipse each other, but not in neat, predictable cycles like in binary systems. Here, the overlaps are relentless and random. Imagine 3 stars aligning perfectly to block a fourth, while 2 others swing wide to flood telescopes with unexpected flares. Then, just as quickly, a 5th star's gravity bends the light from a 6th, lensing it into a temporary brightness spike. The result, a light curve that looks less like a rhythmic pulse and more like a seismograph during an earthquake. Decoding this pandemonium required rewriting the rules of photometry. Traditional models designed for simpler systems collapsed under the complexity. It wasn't until teams deployed machine learning algorithms, training them on millions of simulated scenarios, that patterns began to emerge. The breakthrough came when astronomers realized some fluctuations weren't just random noise but clues. Certain dips in brightness lasted exactly as long as it would take for a star to traverse the disk of another when viewed edge-on from Earth. Others revealed subtle hints about stellar sizes. Faster dips meant compact, dense stars, while slower fades betrayed swollen giants. But the real shock came when researchers noticed anomalies the models couldn't explain. In one system, a star's brightness dropped not by the expected 20% during an eclipse, but by 99%, as if something far larger than another star was passing in front. Follow-up observations pointed to a mind-bending possibility: vast, opaque structures of debris warped by the system's gravity into transient rings or spirals. These weren't ordinary planet-forming disks but shredded remnants of past collisions, stretching across distances that dwarf our entire solar system. Now, astronomers use these extreme light variations as a forensic tool. Like detectives reconstructing a crime scene from scattered clues, they piece together orbits, masses, and even stellar temperatures from the flickers. And with each solved mystery, another emerges, because in a 12-star system, the light show never really ends. It just keeps finding new ways to surprise us. Among all the gravitational madness of duodecuple star systems, some hide an even darker secret: phantom black holes lurking unseen in the stellar chaos. These invisible predators don't reveal themselves through glowing accretion disks or violent X-ray bursts like their active counterparts. Instead, they cloak themselves in silence, their presence betrayed only by the subtle, impossible movements of the stars they shepherd. Imagine watching a dozen fireflies circling an empty patch of night. Their trajectories bend strangely, as if tugged by some unseen hand. That's precisely what astronomers observed in certain 12-star systems where the math refused to add up. Despite precise measurements of all 12 stars' masses and velocities, something massive was missing, an invisible anchor warping the system's core. The explanation: a black hole, not feeding on surrounding matter but resting dormant, its gravity quietly orchestrating the chaos around it. These stealthy giants likely formed from collapsed stars that once belonged to the system, their deaths hidden in the glare of living companions. In one documented case, researchers spent years tracking erratic deviations in a star's orbit before realizing it was looping around empty space at nearly 30% the speed of light, a telltale sign of a black hole roughly 20 times the sun's mass. What's chilling is how easily such objects evade detection. Without the telltale friction of infalling gas to produce X-rays or the lensing effect of a bright background star, they leave no trace beyond their gravitational fingerprints. But their influence is undeniable. Computer reconstructions show dormant black holes acting like cosmic traffic cops, redirecting stellar close calls into stable patterns that prevent total collapse. One simulation revealed how a central black hole's gravity essentially herds stars into separate orbital tiers, some circling tightly near the shadowy core, others flung wide in looping paths. It's a delicate balance. Remove the black hole, and the system implodes into a series of catastrophic collisions within millennia. The discovery raises provocative questions. Could these hidden black holes be the universe's way of preserving extreme multi-star systems that should have torn themselves apart eons ago? And if they're more common than we thought, what other cosmic oddities might be hiding in plain sight, invisible except for the way they bend the world around them? The answers might rewrite our understanding of how the most crowded stellar neighborhoods survive and who or what keeps them in line. For decades, textbooks painted a tidy picture of star formation, giant gas clouds collapsing under gravity, fragmenting into smaller clumps, each birthing a single star or perhaps a binary pair. Duodecuple systems laugh in the face of that simplicity. How does nature cram a dozen stars into a space where conventional wisdom says only 2 or 3 should fit? The answer tears apart old assumptions like tissue paper. Take the classic Jeans instability model, which predicts how large clouds break apart based on density and temperature. In a typical stellar nursery, this process creates orderly separations between newborn stars like bubbles forming in a pot of boiling water, each maintaining polite distance. But in the chaos of a 12-star system's birthplace, something far wilder happens. High-resolution observations of young duodecuples reveal gas filaments braided like cosmic DNA strands, with protostars forming not just at the knots, but along the very threads connecting them. It's as if the entire cloud became a stellar assembly line, cranking out stars shoulder to shoulder before gravity could neatly divide them. Then there's the baffling speed of it all. Traditional star formation is supposed to be a leisurely affair, taking millions of years for a single star to gather its mass. Yet in these crowded systems, stars seem to emerge practically overnight by cosmic standards. Infrared scans show multiple protostars flickering to life simultaneously, their growth spurts fueled by chaotic gas streams ricocheting between them. Picture a dozen faucets all trying to fill from the same hose. Some stars hog the flow while others starve temporarily, creating bizarre size disparities where massive young stars orbit tiny siblings half their age. The real kicker: these systems shouldn't survive infancy. Computer models consistently show that 12 stars forming this close should either merge into a few bloated monsters or scatter like billiard balls after the break shot. Yet here they are, thriving against the odds. Some theorists propose that magnetic fields, often treated as background players in star formation, might act like cosmic bungee cords here, preventing collapses and ejections by tangling around the entire stellar group. Others point to turbulent gas motions that, paradoxically, stabilize the system by constantly redistributing angular momentum. Perhaps most revolutionary is what these systems say about the universe's creativity. We once assumed multi-star systems were accidents, rare flukes of gravitational roulette. But duodecuples suggest nature has a preference for excess, crafting elaborate stellar families wherever conditions allow. Every new discovery in their formation chips away at the idea of a universe that plays by simple, universal rules, revealing instead a cosmos that delights in bending them. The strangest members of any duodecuple star system aren't always the ones born into the chaos. They're the interlopers, the rogue stars that somehow got scooped up by the system's gravity and forced to join its frenetic dance. Imagine a massive stellar fugitive barreling through the galaxy at breakneck speed, only to get snagged by the gravitational net of 12 hungry suns. These captured stars don't play by the rules. Their orbits tilt at bizarre angles, their chemical fingerprints don't match their siblings, and their very presence throws the system into even deeper disarray. Take the infamous case of the Squatter, a blue giant discovered lurking on the fringes of one 12-star system. Spectrographic analysis revealed its composition was all wrong, loaded with elements typically found in much older regions of the galaxy, light years from its current home. Even more damning, its trajectory was hyperbolic, tracing a path that clearly didn't originate within the system. Astronomers pieced together its backstory. This star was a wanderer, likely ejected from a distant cluster millions of years earlier, until a chance encounter with the duodecuple's gravity yanked it into permanent residency. Now it loops around the outer edges like an uninvited guest, its gravity occasionally yanking one of the native stars off course in a cosmic game of tug-of-war. But not all rogue stars are so obvious. Some slip in quietly, disguising themselves among the chaos. In another system, researchers spotted a faint red dwarf with an orbit so stretched and lopsided it resembled a comet's path more than a star's. At first glance, it seemed unremarkable until they noticed its spin rate was nearly triple that of its neighbors. This star wasn't just odd, it was traumatized. The extreme rotation suggested it had endured a brutal gravitational encounter, likely a close call with a black hole or neutron star before being flung across space and captured by its new family. Now it whips around the system's core like a tetherball, its rapid spin a permanent scar from its violent past. The real puzzle is how these outsiders survived their adoption. Conventional models say intruder stars should either destabilize the system entirely or get ejected within a few million years. Yet here they are, persisting for eons. Some systems have even developed bizarre symbiotic relationships with their captives. One particularly lopsided configuration features a captured star acting as a gravitational anchor, its distant orbit subtly stabilizing the inner chaos like a counterweight on a spinning top. It's as if the system itself recognizes the utility of these strangers, bending its own rules to accommodate them. What does this mean for our understanding of stellar communities? It suggests star systems aren't the closed, insular families we once imagined. their dynamic neighborhoods constantly reshuffling their members through chance encounters and galactic upheaval. And if rogue stars can infiltrate even the most complex systems, then nowhere in the galaxy is truly isolated. Every star, no matter how deeply nestled in its cradle, carries the potential to be swept up by a new gravitational family. The cosmos, it seems, loves a good adoption story. At the heart of every star lies a chemical fingerprint, a unique blend of elements forged in its core and scattered by stellar winds. But duodecuple systems don't just break the rules of gravity, they flaunt bizarre chemistry that defies textbooks. Spectrographic analyses reveal stars drenched in elements that shouldn't coexist: rhenium and gold alongside lightweight lithium, or platinum levels 1,000 times higher than our Sun's. These aren't random quirks, they're cosmic crime scenes, hinting at violence on a scale we've barely begun to understand. One system's stars burned with inexplicable amounts of europium, an element so rare it typically forms only in the most extreme supernova. Yet here, multiple stars shared the same anomaly, as if they'd all sipped from the same radioactive soup. The leading theory, a nearby hypernova, a supernova on steroids, detonated with such force that it showered the entire system with heavy elements before most of its stars even finished forming. Picture a stellar nursery getting dusted with the ashes of a catastrophic explosion, its newborn stars absorbing those elements like sponges, but hypernova can't explain everything. Another 12-star cluster showed a baffling surplus of technetium, an element with no stable isotopes. It's the universe's ultimate vanishing act. Technetium atoms decay within mere millennia, yet these stars blaze with fresh supplies as if someone keeps restocking them. The culprit might be as yet undetected neutron star collisions, their merger ejector seeding the system with exotic isotopes. Or worse, these stars could be cannibalizing their own dead, siphoning material from the corpses of collapsed siblings in a macabre stellar recycling program. The weirdest cases defy categorization entirely. Take the zirconium stars, where spectral lines blaze with zirconium oxide signatures so strong they dominate the light spectrum. On Earth, zirconium hides in jewelry. Here, it's an atmospheric pollutant on stellar scales. How does a star become choked with enough zirconium to dim its own light? One hypothesis points to slow-cook nucleosynthesis, layers of the star's atmosphere acting like a cosmic pressure cooker, where atoms capture neutrons one by one over millennia, transmuting into heavier elements without the violence of a supernova. These anomalies aren't just academic curiosities. They rewrite the timeline of stellar evolution, proving that stars in crowded systems don't live or die by the same rules as solitary suns. When 12 stars share a cosmic neighborhood, their fates intertwine in ways that can turbocharge element production, accelerate aging, or even resurrect dead stars with infusions of fresh fuel. It's a reminder that the universe's periodic table has more pages than we've discovered, and duodecuple systems might be holding the pen that writes them. In the cosmic insanity of duodecuple star systems, even death isn't permanent. Astronomers have spotted stars that cheat oblivion, stellar corpses that somehow roar back to life in violent rebirths, defying everything we know about stellar life cycles. These aren't your typical zombie stars like the white dwarfs that steal material from neighbors for temporary fusion revivals. These are full-fledged phoenixes, resurrected from the ashes by the sheer gravitational mayhem of 12-star chaos. Picture a massive star reaching the end of its life, swelling into a red giant before collapsing into what should be a quiet white dwarf or neutron star. Then, just as it fades into darkness, another star's gravity yanks it violently out of retirement. The corpse gets hurled into a close encounter with one of its siblings, triggering an unthinkable chain reaction. Tidal forces rip open its cooled outer layers, exposing raw nuclear material to sudden, catastrophic compression. In seconds, what was dead reignites, not with the steady burn of normal fusion, but in a terrifying thermonuclear detonation that lights up the system like a cosmic flashbang. The first confirmed case was spotted in a 12-star cluster where astronomers witnessed a white dwarf suddenly flaring to 10,000 times its normal brightness for less than a day before fading again. At first, they assumed it was a standard nova, until they realized the dead star had no companion close enough to donate material, the only explanation. A rogue gravitational kick from a passing star had squeezed the white dwarf like a tube of toothpaste, compressing its carbon core just enough to trigger runaway fusion. It was stellar CPR gone horribly right, but the real shock came when researchers found these zombie flares repeating. In one system, a single white dwarf has reignited 7 times in the past century, each outburst separated by unpredictable intervals. The culprit, the other 11 stars keep changing its orbit, altering the timing and intensity of gravitational squeezes it receives. One year, a close pass from a blue giant might rattle it back to life. Decades later, a collective tug from 3 distant stars could do the same. It's death by committee followed by resurrection by chaos. The implications rewrite our understanding of stellar demise. If stars can die and reignite like flickering light bulbs in these systems, how many other cosmic corpses might be biding their time, waiting for the right gravitational nudge? And what does this mean for the heavy elements these explosions scatter into space? Every time a zombie star flares, it cooks up bizarre isotopes in conditions no lab could replicate, seeding the cosmos with chemistry we've barely begun to catalog. It's a reminder that in the universe's most crowded neighborhoods, even the laws of life and death are up for negotiation. In the gravitational tangle of a duodecuple star system, some stars don't just orbit, they become cosmic whirligigs, spinning so fast they stretch into oblate monstrosities, their equators bulging outward like overfilled water balloons. These aren't your average rotating stars. They're the universe's equivalent of figure skaters pulling endless, violent pirouettes, accelerated to speeds that defy physics as we know them. The record holder, a star in one 12-star system, clocked at nearly 2 million miles per hour at its equator, so fast it completes a full rotation in under 2 hours. For comparison, our sun takes a leisurely 25 days. What forces could possibly whip a star into such a frenzy? The answer lies in the relentless tidal bullying of its 11 siblings. Each close pass from another star acts like a gravitational slap, transferring angular momentum in a celestial game of hot potato. Picture a child spinning on a playground merry-go-round while friends keep shoving them faster. Except here, the child is a seething ball of plasma larger than 100 Earths, and the friends are other stars whose gravity tugs at it from all directions. Over millennia, these constant nudges ratchet up the spin until the star's own centrifugal force nearly overcomes gravity's grip, threatening to fling its outer layers into space like a dog shaking off water. The consequences are as dazzling as they are destructive. These rapid rotators become factories of extreme radiation, their magnetic fields twisting into knots that unleash torrents of X-rays and ultraviolet flares. Some develop equatorial deformation belts, where material stretches so thin it glows hotter than the core, creating bizarre double-temperature surfaces. Others spew continuous stellar hurricane supersonic winds of ionized gas that stream from their poles in tight, luminous jets, but the real surprise: these stars shouldn't survive their own speed. Classical models predict they'd tear themselves apart long before reaching such velocities, yet here they are, balanced on the knife's edge of stability. The secret might lie in their chaotic environment. In a duodecuple system, gravitational interactions are so frequent that they don't just spin stars up, they also occasionally break them, preventing total disintegration. It's a cosmic balancing act where chaos and order collide, proving once again that the universe's most extreme laboratories refuse to follow the rules. And then there's the lingering mystery of the spin outliers, stars rotating even faster than tidal theory allows. Some show evidence of past collisions, where a glancing merger with another star dumped extra angular momentum like a turbo boost. Others might be feasting on stolen material from nearby companions, gulping down gas that carries rotational energy. Whatever the cause, these hyperspinners challenge our fundamental understanding of stellar limits, offering front-row seats to physics pushed to its breaking point. If stars can survive this kind of punishment, what other impossibilities might be hiding in the chaos? Among the swirling chaos of 12 star systems, there's a gravitational mystery that defies even the wildest theories. Systems that weigh more than they should. When astronomers calculate the combined mass of all 12 stars, then measure how they tug on one another, the numbers refuse to add up. Something invisible, something massive, is lurking in the shadows, bending orbits and warping starlight without leaving a trace. Take one notorious system where the outer stars whip around the core at speeds that should send them flying into deep space, yet they stay bound as if gripped by an unseen fist. The math says there's at least 30% more mass in the system than the stars account for, equivalent to packing 3 extra suns into the mix, but without the light or heat. At first, researchers assumed it was a simple case of dim, failed stars hiding in the glare, brown dwarfs too faint to spot, but infrared scans came up empty. Then came the next unsettling possibility: rogue planets, hundreds of them, each the size of Jupiter. Yet even that couldn't explain the sheer scale of the discrepancy. This is where the theories take a darker turn. Some astrophysicists argue these systems might be riddled with dark matter, the universe's most elusive substance, which outweighs visible matter 5 to 1 but refuses to interact with light. Normally, dark matter spreads diffusely across galaxies, but simulations suggest duodecuple systems could act like cosmic spiderwebs, trapping dense clumps of it in their gravitational folds. If true, these 12-star chaos factories might be accidental dark matter detectors, revealing pockets of the invisible stuff we've struggled to find elsewhere. Then there's the even wilder option: hidden black holes. Not the monster at the system's core, but smaller, wandering ones. Stellar mass black holes left over from ancient supernova, now drifting unseen between the stars. Their gravity would yank on nearby suns like invisible puppet strings, explaining erratic orbits that flicker unpredictably over decades. One team even proposes a black hole archipelago, multiple dark objects spaced throughout the system, their positions shifting as stars jostle them like icebergs in a churning sea. But the most tantalizing clue comes from gravitational microlensing events, brief flashes when something unseen magnifies the light of a background star. In one system, these flashes happen far too often, as if countless compact objects, each too small to be a star but too heavy to be planets, are scattered through the system like invisible landmines. Are they primordial black holes from the universe's birth? Exotic quark stars that theory predicts but we've never seen? Or something even stranger, a form of matter so alien it rewrites the rules of physics? What makes this missing mass so provocative isn't just its existence, it's how it reshapes the system's fate. That extra gravity acts like cosmic glue, preventing the stars from tearing each other apart even as their orbits grow more tangled. Without it, simulations show these systems should have disintegrated eons ago. Instead, they persist, their hidden scaffolding hinting that the universe's most extreme stellar neighborhoods might owe their survival to the very things we can't see. Every unexplained wobble, every too fast orbit is a breadcrumb trail, and it's leading us straight into the dark. Pulsars are supposed to be the universe's most precise clocks, spinning neutron stars that beam radiation with metronomic regularity, their pulses so predictable you could set your watch by them. Or at least that's how they behave when left alone. Drop one into a duodecuple star system and all bets are off. Astronomers have observed pulsars in these chaotic environments doing things that should be impossible, suddenly speeding up for no reason, skipping beats like a scratched vinyl record, or even shutting off entirely for months before sputtering back to life. These aren't minor hiccups, they're full system malfunctions that strike at the heart of neutron star physics. Take the case of PSRJ 1911+14, a millisecond pulsar nestled in a 12-star maelstrom. For years, its pulses arrived every 3.2 milliseconds like clockwork until one day the rhythm stuttered. Over the course of a week, its spin rate inexplicably jumped by 12%, as if some cosmic hand had given it a violent twist. Then, just as abruptly, it slowed back down. Traditional explanations like material falling onto the pulsar's surface couldn't account for the sheer violence of the change. The leading theory now points to gravitational tides from nearby stars warping the pulsar's crust like a spoon bending in a bowl of gelatin, momentarily altering its moment of inertia. But the real head-scratchers are the blackout events. In one system, a pulsar designated XT47 suddenly went silent for 416 days, its radio beacon vanishing as if switched off. Just as mysteriously, it reactivated, but with pulses now arriving 7 microseconds earlier than before. The best explanation: the entire neutron star might have undergone a starquake, its rigid crust cracking under strain from the system's gravitational tides. When the crust rebounded, the pulsar's spin axis could have shifted minutely, changing how its beams intersect with Earth. What makes these anomalies so troubling is that they contradict decades of pulsar research. Isolated neutron stars behave like well-oiled machines. Their timing irregularities are subtle, caused by gradual slowdowns or the occasional glitch from crustal adjustments. But in duodecuple systems, the rulebook gets shredded. Some pulsars here show anti-glitches, unexpected slowdowns instead of speed-ups, while others exhibit timing noise so erratic it looks almost intentional. The wildest example might be PSRK29, whose pulse delays map perfectly to the orbital positions of 3 nearby stars, as if it's being puppeteered by their gravity in real time. The implications stretch far beyond these systems. If gravitational chaos can rewrite how pulsars behave, what else might we be missing about neutron stars in quieter environments? And could these glitching pulsars be trying to tell us something fundamental about the nature of extreme matter, hinting at exotic states of quark-gluon plasma or hyperfluid cores beneath their crusts? For now, every erratic pulse is both a puzzle and a clue, reminding us that even the universe's most reliable timekeepers can't resist the pull of celestial anarchy. In the swirling maelstrom of a 12-star system where gravity seems to play by no rules at all, there's a phenomenon that defies logic: stable binary pairs. These aren't just any orbiting twins, they're stars locked in such tight, perfect harmony that they practically ignore the pandemonium around them. Picture two dancers in the middle of a mosh pit, moving in flawless sync while chaos erupts on all sides. That's the enigma astronomers face when they stumble upon these impossible duos nestled within duodecuple systems. How does a binary pair maintain its bond when 11 other stars are constantly yanking at it? One particularly baffling case involves 2 red dwarfs circling each other so closely that their surfaces nearly touch, completing an orbit in just under 4 hours. What's astonishing isn't their speed, it's their resilience. Over decades of observation, their rhythm hasn't wavered, even as massive blue giants whiz past at distances that should have ripped them apart. The secret might lie in their simplicity. Unlike their more massive neighbors, these stars have minimal magnetic fields and sluggish stellar winds, creating a kind of gravitational bubble where outside disturbances struggle to penetrate. But not all stable pairs are so demure. Another system boasts a binary of hyperactive T-Tauri stars, cosmic toddlers still in their tantrum phase, spewing plasma and twisting magnetic fields. Logic says their violent outburst should make them easy prey for disruptive forces, yet they've clung together for millions of years, the key their shared cradle of gas. Infrared scans reveal a thick disk of material still encircling the pair, acting like a shock absorber against external tugs. Every time a passing star disturbs them, the disk redistributes the energy, smoothing out the chaos before it can break their bond. Then there's the real head-scratcher binaries that shouldn't exist at all. In one system, a neutron star and a main sequence star orbit so closely that the latter's outer layers are being siphoned away, forming a glowing bridge of stolen material. Normally, such a lopsided relationship would destabilize quickly, with the neutron star either consuming its companion or flinging it away. Yet here they persist, locked in a gravitational détente. The likely explanation, the other 10 stars in the system, rather than tearing them apart, actually provide a stabilizing influence. Their combined gravity creates a sort of tidal lock that counterintuitively keeps the pair balanced, like a spinning top that wobbles but never falls because of the very forces trying to knock it over. What these paradoxical pairs reveal is a hidden order beneath the apparent chaos. For all their violence, duodecuple systems might have unseen mechanisms, gravitational resonances, magnetic buffers, or even sheer momentum that protect certain bonds from breaking. It's as if the universe, having engineered the ultimate stellar free-for-all, secretly planted a few rules to keep the madness from descending into total anarchy. And if stars can find stability in such extreme environments, what other cosmic impossibilities might be waiting to rewrite the rules? Watching a duodecuple star system in motion is like trying to follow 12 fireflies performing an intricate waltz inside a tornado. The orbits don't follow neat, predictable ellipses. They twist into pretzel shapes, spiral outward only to snap back, or suddenly swap places in a gravitational game of musical chairs. Astronomers tracking these systems have witnessed stars pirouetting around one pair of companions, only to be snatched away by a third star's pull mid-orbit, as if some unseen choreographer keeps rewriting the dance steps in real time. Take the bizarre case of the celestial tarantella, a 12-star cluster where 3 separate pairs of stars orbit a central core at different inclinations, while 6 outliers weave between them in a pattern resembling a braided rope. Over a decade of observations, one star, dubbed the Tramp, completed what should have been a stable loop around its binary partners, only to be hijacked by a passing trio's gravity. Instead of resisting, it seamlessly joined their formation, leaving its original companions to close ranks behind it as if nothing had happened. This wasn't a violent collision or ejection, but a graceful cosmic handoff orchestrated by the system's collective gravity. The mechanics behind this chaos reveal a startling truth. These systems aren't just random scrambles. They operate on a hidden hierarchy where stars temporarily pair up in smaller, stable configurations before the group's combined gravity reshuffles the deck. Computer simulations show fleeting moments of symmetry, like the triple waltz, where 3 binaries orbit a shared center, their motions locked in resonance for centuries before disruption. Other times, a single star acts as a gravitational pivot, its steady pull briefly taming the pandemonium like a conductor steadying an orchestra. What's truly mesmerizing is how these dances play out over time. In one system, astronomers reconstructed orbital paths spanning millennia, revealing a recurring pattern where every 12,000 years, the stars align in a near-perfect dodecahedron, a 12-sided geometric marvel, before exploding back into chaos. It's as if the system has a memory, cycling through phases of bedlam and fleeting order. But the most jaw-dropping realization, this isn't just celestial spectacle, it's survival. The same gravitational exchanges that look like reckless abandon actually prevent catastrophe. Stars stealing momentum from one another avoid deadly collisions, while those flung outward often loop back with energy to spare, like boomerangs in zero gravity. Even the wildest maneuvers serve a purpose, keeping 12 massive objects from crashing together in a fireball of mergers and supernova. The universe, it seems, favors creative chaos over tidy destruction. And in these starry ballets, every reckless spin and stolen orbit is a step toward an improbable equilibrium. one of the most baffling discoveries about duodecuple star systems isn't just their chaotic orbits, it's their impossible birth certificates. Normally, stars in a cluster form together from the same collapsing gas cloud, making them celestial twins with nearly identical ages. But some 12 star systems laugh in the face of this rule, mixing ancient red giants with sprightly young stars as if a retirement home suddenly hosted a kindergarten class. The age gaps aren't minor. We're talking stellar grandparents billions of years older than their newborn neighbors, sharing the same gravitational playground. Take the infamous time warp cluster, where spectroscopy revealed 3 oxygen-rich red giants that must have formed over 12 billion years ago, alongside a group of blazing blue stars less than 50 million years young. The older stars show heavy elements typical of the early universe, while the youngsters are practically drenched in lithium, an element their elders should have burned off eons ago. It's like finding a medieval knight's armor hanging next to a spacesuit in the same closet. How does such a cosmic age gap happen? The leading theory involves a brutal game of stellar capture. Imagine an ancient star cluster, its original members long since faded or drifted apart. Then, a dense molecular cloud drifts into the neighborhood, collapsing to birth fresh stars right in the midst of these elderly survivors. Gravitational chaos ensues, with the young star's energy puffing up the gas cloud like a souffle, while the old star's gravity molds the new arrivals into improbable orbits. Over millennia, they become a dysfunctional but bound family, their age differences frozen in celestial amber. But there's an even wilder possibility. Some systems might be actively birthing new stars long after their initial formation. Infrared telescopes have spotted dense knots of gas stubbornly clinging to existence amid these systems, shielded from dispersal by the collective gravity of 12 stars. These gas pockets could collapse under their own weight at any time, sparking fresh rounds of star formation billions of years after the first generation lit up. Picture a cosmic matryoshka doll, where each layer represents a new era of stellar birth crammed into the same congested space. The implications rewrite what we know about star formation timelines. If multiple generations can coexist in one system, then the universe's stellar nurseries might be far more flexible and far messier than we ever imagined. These age-defying systems prove that star formation isn't a one-time event, but an ongoing process that can reboot itself under the right conditions. And if stars with billions of years between them can share the same gravitational address, what other cosmic impossibilities are we just beginning to uncover? In the cosmic hall of mirrors that is a duodecuple star system, sometimes what you see isn't just improbable, it's physically impossible. Telescopes have captured jaw-dropping snapshots of these systems appearing to host not 12, but 13, 14, even 15 stars. The catch: some of those stars don't actually exist. They're phantom suns conjured into view by the system's own gravitational witchcraft, a phenomenon so convincing it's fooled both human observers and AI algorithms designed to catalog celestial objects. The illusion begins with gravitational lensing, where the combined pull of multiple stars warps spacetime like a funhouse mirror. When light from a background star passes through this distorted region, it bends around the system's stars, splitting into multiple images or smearing into elongated arcs. From Earth's perspective, these distorted beams converge to form perfect pinpoints of light indistinguishable from real stars. In one notorious case, a 12-star system in Cygnus appeared to gain 3 new members overnight. Follow-up observations revealed the imposters were actually a single red giant located 50,000 light-years behind the system, its light triplicated by the duodecuple's lensing effect. But the real mind-bender: these phantom stars don't just sit still, they move. As the foreground stars shift positions, their gravitational lenses flex, causing the apparitions to drift across the sky at impossible speeds. In 2018, astronomers tracking a 12-star cluster watched in disbelief as a rogue star seemed to accelerate to 20% the speed of light before vanishing. The explanation was both simple and surreal. The illusion wasn't accelerating, the alignment between background star, lensing stars, and Earth was shifting, stretching the light's path like a cosmic rubber band. The most deceptive illusions occur when lensing magnifies stars that would otherwise be too faint to see. One system's 13th star turned out to be a magnification of a brown dwarf 100 times dimmer than the Sun, its light amplified by a perfect alignment of 4 foreground stars acting as a natural telescope. For 73 years, this faint smudge was catalogued as a bona fide member until orbital motion broke the lensing chain and the star winked out of existence. What makes these illusions so valuable isn't just their sleight of hand, it's what they reveal about the systems creating them. By analyzing phantom stars' movements, astronomers can map the invisible scaffolding of gravity holding these chaotic systems together. Each mirage acts like a probe, exposing mass distributions and dark matter halos no telescope could see directly. And occasionally, they uncover genuine cosmic secrets. One phantom's distorted spectrum betrayed the presence of a previously unknown galaxy lurking billions of light-years behind the Duodecuple system, its light bent and reshaped into the perfect celestial disguise. In the end, these stellar doppelgangers are a reminder that even our most advanced instruments don't show us reality, just light that's crossed an obstacle course of gravitational tricks. And in a universe where space itself can twist starlight into lies, seeing isn't always believing sometimes. It's just the first step in unraveling a much deeper mystery. If you thought 12 star systems were chaotic just because of their gravity, wait until you see what happens when their magnetic fields collide. Each star in these cosmic tangles generates its own magnetic field, some modest like our Sun's, others so intense they could rip atoms apart at 1,000 miles away. Now cram them all together in a space where some stars orbit closer than Mercury is to the Sun, and you've got a recipe for electromagnetic pandemonium unlike anything else in the known universe. Take one system where 3 stars, a pulsar, a flare star, and a chemically peculiar blue giant orbit each other in a space narrower than Jupiter's distance from the Sun. The pulsar's lighthouse beams of radiation sweep through the blue giant's magnetosphere like a cosmic blender, triggering bursts of X-rays so powerful they briefly outshine the combined light of all 12 stars. Meanwhile, the flare star's sporadic eruptions send shockwaves through this already volatile mix, twisting magnetic field lines into knots that snap back with enough force to accelerate particles to near light speed. Telescopes have recorded these magnetic reconnection events, unleashing tera-electronvolt gamma rays, energy levels typically seen only in supermassive black holes. The real nightmare begins when these fields entangle on larger scales. In another system, astronomers mapped a sprawling web of interconnected magnetism linking 10 of the 12 stars, a sort of stellar spiderweb where a flare on one star could trigger sympathetic eruptions in others light days away. Charged particles surfing these field lines create glowing bridges visible in radio wavelengths, turning the entire system into a flickering neon sign writ large across the galaxy. But the crown jewel of magnetic madness has to be the dance of the polar caps. Some stars in these systems have fields so distorted by their neighbors that their magnetic poles no longer align with their rotational axes. Instead, the poles wander across the stellar surface like lost compass needles, sometimes even flipping entirely in weeks rather than the millennia our Sun takes. One particularly extreme case showed a star with 4 distinct magnetic poles, each one locked in a tug of war with different stellar neighbors, creating patches of surface where the magnetic field strength spiked to 50,000 times Earth. What makes this electromagnetic chaos so revealing is how it challenges our understanding of stellar magnetism. Single stars behave predictably, their fields wax and wane in orderly cycles. But pack a dozen together, and their fields become living entities constantly evolving, merging, and rebelling against each other in ways supercomputers struggle to simulate. Every tangled field line and rogue particle beam is a clue to questions we're only beginning to ask. How does energy propagate through such systems? Could these electromagnetic storms seed exotic particle physics we can't recreate on Earth? And most tantalizingly, if intelligent life somehow arose here, could they harness this raw magnetic fury as a power source far beyond anything we've dreamed? The answers might rewrite not just stellar physics, but our place in the universe itself. The cosmos has a way of preserving its most violent moments not in scars or debris, but in echoes. In one extraordinary Duodecuple system, astronomers witnessed a supernova explosion so powerful that its light didn't just fade into oblivion, it bounced. Years after the initial blast, faint ripples of light began reappearing, illuminating hidden corners of the system like a celestial echo chamber. This wasn't just a delayed afterglow, it was a cosmic replay, revealing secrets about the system's structure that would have otherwise stayed locked in darkness. The event started predictably enough. A massive star at the system's edge collapsed under its own weight, detonating in a supernova bright enough to outshine its 11 siblings combined. Telescopes captured the initial flash, a brilliant spike of ultraviolet and X-rays before it dimmed over weeks. But just when astronomers thought the show was over, something bizarre happened. 3 years later, a faint ring of light emerged around the explosion site, expanding outward like a ripple in a pond. Then another appeared, and another. Each ring was a perfect replica of the original supernova's light curve, but shifted slightly in color and timing. These light echoes occur when the initial explosion's radiation slams into distant dust clouds or gas filaments, heating them until they re-emit the light sometimes decades later. Normally, these echoes are faint and scattered, but in this 12-star system, the echoing light painted a precise roadmap of the unseen. The rings weren't random, they traced concentric shells of debris left behind by ancient stellar collisions, their curves betraying the gravitational tug of hidden stars. One particularly bright echo revealed a previously unknown gas torus, a donut-shaped cloud wrapped around 2 central stars, likely ejected during a near-miss encounter millennia ago. The real breakthrough came when scientists realized the echoes weren't just reflecting the supernova's light, they were distorting it. As the light bounced off dust clouds at different angles, subtle shifts in its spectrum exposed magnetic fields and turbulence invisible to direct observation. One echo's polarization pattern hinted at a vast magnetic bubble surrounding 3 stars, warped by their orbital dance. Another's faint redshift suggested the presence of a high-speed jet, perhaps from a neutron star or black hole plowing through the system's outskirts. But the most haunting revelation was temporal. By tracking the echo's expansion rates, astronomers reconstructed a 3D map of the system's dust lanes, proving some structures hadn't changed in position for over 500,000 years. That stability amid the system's chaos was the real shock. How could such delicate filaments survive the gravitational maelstrom of 12 stars? The answer might lie in dark matter, invisible halos anchoring the gas against disruption, or in some self-reinforcing magnetic architecture we've yet to understand. What began as a fleeting stellar death became a decades-long dissection of cosmic infrastructure. Every echo was a flashbulb illuminating another hidden corner, turning a single cataclysm into the ultimate diagnostic tool. And somewhere in that labyrinth of reflected light, there's likely another echo still traveling, waiting to hit another unseen wall of dust, ready to tell us something new about the universe's most crowded stellar neighborhoods. Dust in space isn't supposed to act this way. In most star systems, debris follows predictable patterns, settling into neat disks around single stars or gently drifting outward when nudged by stellar winds. But drop that same dust into a Duodecuple system and all bets are off. Here, interstellar grit doesn't just float passively, it twists into bizarre formations that look more like abstract sculptures than cosmic leftovers. Some strands spiral like DNA around multiple stars, others clump into lopsided rings that pulse eerily when stellar winds buffet them, and a few even form transient bridges connecting stars light days apart. Take the case of the dust serpent, a filamentary cloud winding through one 12-star system like a cosmic sidewinder. Infrared telescopes revealed this structure isn't just drifting, it's actively circulating, carrying material from the outer reaches toward the system's core at speeds that defy simple gravitational explanations. The leading theory suggests it's caught in a cosmic tug-of-war, with competing stellar winds from 4 different stars sculpting it into this twisted river of debris. At one point, the serpent even appears to feed a fledgling protoplanetary disk around a young star, funneling fresh material into what should have been a starving formation zone. Then there's the mystery of the vanishing rings. In another system, astronomers observed 3 concentric dust rings orbiting a central star pair, until a close pass from a third star sent the outermost ring rippling outward like a stone dropped in water. Over just 17 years, the ring stretched into an elliptical arc before seemingly dissolving into nothing. The shock came 5 years later, when the vanished material abruptly reappeared as a diffuse glow near a different star altogether, as if the system had teleported its own debris. The likely culprit, hidden magnetic fields generated by the chaotic interplay of stellar winds, temporarily trapped and redirected the dust along invisible force lines before releasing it elsewhere. But the real enigma is what this dust reveals about planet formation, or rather, the shocking persistence of it in such hostile environments. Conventional wisdom says planets shouldn't stand a chance here, where gravitational tides would rip apart, forming protoplanetary disks long before worlds could coalesce. Yet ALMA telescope observations have spotted at least 4 systems where dust has organized into dense, structured spirals, the telltale nurseries of planet birth. Even more bizarre, some of these disks show chemical gradients normally seen in quiet, single-star systems, with water, ice, and organic molecules concentrated in their inner regions despite the surrounding pandemonium. What does this mean? That dust in these extreme systems isn't just surviving the chaos, it's exploiting it. Simulations show how passing stars can actually herd debris into stable pockets, their gravity acting like cosmic sheepdogs corralling material into protected zones. Other models suggest electromagnetic forces from tangled stellar magnetospheres might create temporary, safe rooms where dust can clump undisturbed for millennia. And in the most tantalizing cases, astronomers suspect some disks are being actively replenished their destruction by one star balanced by fresh infalls of materials stirred up by another, creating a precarious but enduring cycle of creation and destruction. The implications ripple far beyond these 12-star oddities. If dust, and by extension, planets, can form and persist in such extreme environments, then the universe might be far more prolific at building worlds than we ever dared imagine. And hidden within these turbulent dust clouds could lie answers to an even bigger question. In a cosmos where chaos seems to reign, how does anything manage to hold itself together at all? X-ray telescopes scanning Duodecuple star systems sometimes catch eruptions so violent they rewrite the rules of high-energy astrophysics, flares blasting with the power of 1,000 suns, vanishing within hours, then reappearing years later with no warning. These aren't your garden-variety stellar flares or pulsar emissions. There's something far stranger, X-ray storms that crackle through these systems like celestial lightning, their origins buried in layers of gravitational and magnetic chaos that even our most advanced models can't fully unpack. One particularly violent event lit up detectors in 2017 when a 12-star system in Orion unleashed an X-ray burst brighter than the Milky Way's central black hole. For 43 minutes, it flooded space with high-energy photons, then cut off as abruptly as it began. The kicker, no visible star in the system matched the eruption's location. Follow-up observations pointed to an empty patch of space between three tightly orbiting stars, a place where nothing should exist capable of generating such energy. The leading explanation, a hidden microquasar, a stellar mass black hole or neutron star devouring material from an unseen companion. Its accretion disk tilted at such an extreme angle that it's invisible in optical light but periodically flips into view when jostled by nearby stars' gravity. But the real mystery is the storm's unpredictability. In most X-ray binaries, eruptions follow rough timetables tied to the donor star's orbit. Here, the bursts arrive like uninvited guests, sometimes clustering in rapid-fire succession, other times vanishing for decades. One system's X-ray flares appear synchronized with the orbits of two distant stars, as if their gravity tugs on hidden structures light days away, triggering avalanches of infalling material. Another's outbursts correlate with planetary alignments in our own solar system, an absurd coincidence that had researchers triple-checking their math before conceding it might be pure cosmic irony. The energy spectra of these eruptions deepen the puzzle. Some show telltale ion emission lines indicative of matter spiraling into a black hole at relativistic speeds. Others blast pure, featureless continua, the signature of particle acceleration in tangled magnetic fields, so intense they make neutron stars look tame. A handful even exhibit quantum electrodynamic effects typically seen only near magnetars, with photons so densely packed they begin interacting with each other mid-flight. What makes these storms so revolutionary isn't just their violence, it's what they reveal about the system's hidden scaffolding. Each flare acts like a flashbulb, illuminating otherwise invisible structures. One eruption's X-rays scattered off a previously undetected disk of ionized gas wrapped around 4 stars. Another's afterglow exposed vast magnetic loops arcing between stellar pairs, structures so large they'd span from the Sun to Pluto if transplanted to our solar system. The most unsettling implication, we might be witnessing real-time cosmic evolution. Some theorists suggest these X-ray cataclysms are birth pangs, signs of compact objects forming through channels no one predicted. Imagine a white dwarf repeatedly ping-ponged between stellar neighbors, gaining just enough mass with each gravitational slingshot to eventually collapse into a neutron star without a supernova. Or a black hole born not from a dying star, but from the direct merger of 2 brown dwarfs squeezed together by the system's tides. Every erratic burst challenges our definitions of what's possible. If empty space between stars can suddenly erupt with the energy of a supernova, if hidden objects can lurk undetected until the perfect gravitational nudge makes them scream in X-rays, then what other monsters might be hiding in plain sight, waiting for their moment to shake the heavens? In the cosmic free-for-all of a duodecuple star system, some stars don't just dance with their neighbors, they feast on them. Picture a massive blue giant circling a smaller, aging star, its gravity peeling away layers of stellar material like a cosmic vulture stripping flesh from bone. This isn't just poetic imagery. Astronomers have witnessed stars in 12 star systems draining their companions at rates that defy physics, creating some of the most violent and unpredictable stellar relationships in the known universe. The mechanics of this vampirism are as brutal as they are mesmerizing. When 2 stars orbit dangerously close in these crowded environments, the larger star's gravity can stretch its companion into a teardrop shape, creating a plasma bridge between them. Gas from the victim star's outer layers gets siphoned through this bridge at speeds approaching 1,000,000 miles per hour, spiraling onto the predator star in an incandescent whirlpool. But here's where the chaos of a 12-star system twists the scenario into something even more extreme. Unlike isolated binary systems where this process might proceed steadily, the constant gravitational jostling from 10 other stars turns this cosmic bloodletting into a spasmodic frenzy. Material transfers happen in violent bursts rather than steady streams, with some stars gulping down entire Jupiter-sized chunks of their neighbors in single orbital passes. One particularly gruesome case study involves a B-type star dubbed the Gulper, which astronomers observed consuming its red giant companion at a rate that should have torn both stars apart. Normally, such extreme mass transfer would cause the predator star to bloat and shed the stolen material in luminous eruptions, but in this duodecuple system, something stranger happened. Every time the Gulper began to overflow from its stellar feast, a passing third star's gravity would yank the excess material away, forming a temporary accretion disk that then funneled the plasma onto yet another star in the system. It became a grotesque game of hot potato, with stellar matter getting passed between multiple stars before finally being ejected entirely in a nova-like blast visible across the galaxy. The aftermath of these feeding frenzies can be even more spectacular than the act itself. Some vampire stars grow so massive from their stolen meals that they skip entire evolutionary stages, rocketing from main sequence stars to blue supergiants in mere millennia, a process that normally takes millions of years. Others accumulate just enough extra mass to undergo supernova imposter eruptions, where they nearly destroy themselves in pseudo-explosions that eject their stolen atmospheres into space. Radio telescopes have detected enormous plasma loops stretching between stars in these systems, fossil remnants of past feeding events frozen in magnetic amber. But perhaps the most unsettling discovery is how these vampiric relationships can reshape entire systems. When one star rapidly gains or loses mass, the delicate gravitational balance holding all 12 stars together gets thrown into turmoil. Computer simulations show that a single extreme mass transfer event can trigger chain reactions lasting centuries, stars swapping places in the orbital hierarchy, tightly bound pairs suddenly flung apart, or even multiple stars being ejected entirely. It's a reminder that in these crowded stellar metropolises, no star's fate is truly its own. Every vampiric bite, every stolen breath of stellar plasma sends ripples through the cosmic web that binds them all together, proving once again that in a duodecuple system, survival isn't just about strength, but about knowing when to feed and when to flee. Among the swirling chaos of 12 star systems lies an unexpected gift for physicists, a natural laboratory for probing the deepest mysteries of quantum gravity. These cosmic maelstroms generate conditions so extreme they warp spacetime itself, creating environments where the fabric of reality might reveal secrets no particle collider on Earth could ever reproduce. Picture the seething boundary between two neutron stars locked in a death spiral, their combined gravity squeezing matter to densities where atoms surrender to quantum foam. Or the twisted magnetic fields where three stellar magnetospheres collide, potentially birthing fleeting particles that only exist when gravity and quantum forces clash at their limits. The real magic happens in the system's gravitational tides, not the gentle lunar pulls we know, but violent spacetime distortions from a dozen massive objects yanking in different directions. At certain orbital intersections, calculations suggest space might fracture into microscopic bubbles of alternate geometry, fleeting zones where Einstein's smooth continuum gives way to the pixelated froth predicted by loop quantum gravity. In 2022, researchers analyzing light from one such system detected anomalous photon scattering that matched simulations of space-time granularity, as if starlight had briefly ricocheted off the quantum structure of gravity itself. Then there's the black hole factor. Many of these systems harbor hidden stellar mass black holes, their event horizons acting as natural particle accelerators. When two such holes orbit closely, their mutual gravitation could generate entangled spacetime vortices, regions where quantum information gets imprinted on passing radiation in ways that might finally bridge general relativity with quantum mechanics. One team even speculates that certain X-ray flickers observed in these systems could be signatures of Hawking radiation, the elusive quantum glow predicted to escape black holes, amplified by the surrounding stellar chaos into detectable bursts. What makes these systems indispensable is their sheer unpredictability. While human-built colliders meticulously control conditions, duodecuple chaos offers something far more valuable: random, violent configurations no engineer could design. A passing star might pinch a magnetic field line with just enough force to spawn a virtual black hole for a nanosecond. Colliding stellar winds could generate shockwaves dense enough to briefly crystallize spacetime into higher dimensions. Even failed stellar collisions where two stars nearly merge but rebound might create gravity waves with quantum harmonics hidden in their ripple patterns. The ultimate prize: catching gravity in the act of behaving quantum mechanically. Most theories predict this should manifest as subtle fluctuations in how light redshifts near extreme masses, or as statistical anomalies in particle decay rates during gravitational surges. 12 star systems provide countless test cases, their ever-shifting gravity wells acting like a flipbook of possible quantum gravity interactions. Some researchers are already designing AI to mine decades of observational data for these telltale fingerprints, because if quantum gravity leaves a mark anywhere, it's in the places where stars themselves bend the rules past breaking point. Among the wildest theories surrounding duodecuple star systems is the spine-tingling possibility that some might host technology built by civilizations far beyond our own. The speculation erupted when astronomers noticed bizarre, non-periodic dimming events in certain 12-star clusters' light patterns so irregular they defied all known natural explanations. Unlike predictable eclipses or stellar pulsations, these dips occurred at random intervals, sometimes blotting out staggering percentages of a star's light for days before abruptly snapping back to normal. The strangest part: the light curves didn't match anything in the astrophysical playbook. No cometary swarms, no dust clouds, no planetary debris fields could explain the sheer scale and asymmetry of these events. One infamous case centered on a system where 3 stars showed coordinated dimming, almost as if something enormous was passing between them and Earth in precise, unnatural intervals. The dips weren't smooth like a transiting planet. They featured sharp, angular edges and secondary fluctuations that resembled, to some researchers, unease the light patterns one might expect from vast orbiting structures with complex geometries. The internet promptly combusted with talk of Dyson swarms, hypothetical megastructures built by advanced civilizations to harness stellar energy, though the scientific community urged caution. After all, nature has fooled us before with perfectly natural phenomena that only seemed artificial at first glance. Skeptics quickly pointed to more plausible explanations. Perhaps immense rings of shattered planetesimals, warped by the system's chaotic gravity into lopsided formations, were casting these irregular shadows. Or maybe collisions between protoplanetary debris disks had spawned temporary, light-blocking structures millions of miles across. Some theorists even proposed exotic plasma dynamics, magnetic flux tubes or star-grazing nebulae behaving in ways not yet documented. The most compelling natural hypothesis involves gravitational lensing storms, where the combined pull of 12 stars distorts passing light from background objects in ways that mimic artificial megastructures when viewed from our perspective. Yet the tantalizing uncertainties linger. In one system, the dimming events coincided with narrowband radio emissions at frequencies some argue are suspiciously optimized for interstellar communication. Another exhibited thermal anomalies. The shadowed regions radiated slightly more infrared light than expected, as if whatever was blocking the starlight was absorbing and re-emitting energy rather than simply obscuring it. These oddities, while far from proof, keep the debate alive in certain scientific circles. The sobering reality: if these were megastructures, they'd dwarf anything humanity could conceive. The light patterns suggest objects spanning millions of miles, engineering on a scale that would require mastery over energies and materials beyond our physics. And that's the real fascination. Even if these phenomena turn out to be purely natural, they're stretching our understanding of what's possible in heavily populated stellar systems. Whether we're glimpsing alien technology or simply undiscovered astrophysics, one thing's certain: duodecuple star systems keep finding ways to challenge our assumptions about how the universe works. And who or what might be out there rewriting the rules? The gravitational madness of duodecuple star systems doesn't just bend space, it twists time itself into knots. Picture a cosmic stopwatch ticking at different rates across the system, where a single hour near one star might equal days near another. This isn't science fiction, it's hard physics predicted by Einstein's theory of general relativity, amplified to extremes in these 12-star maelstroms. Near the system's most massive stars, or worse, near hidden black holes, time slows so dramatically that astronauts orbiting there would return to find centuries had passed in the wider galaxy. Take a hypothetical scenario where two stars orbit a shared center. One a neutron star packing twice the sun's mass into a city-sized sphere, the other a bloated supergiant 20 times more massive but spread across an enormous volume. The neutron star's extreme density creates a gravitational well so deep that clocks on its surface would run 34% slower than those near its diffuse companion. Now multiply this effect across 12 stars of varying masses and densities, some whipping around each other at relativistic speeds, and you've got a time-warping labyrinth where the very concept of now fractures across light years. The most mind-bending implications emerge near compact objects like neutron stars or black holes. In one simulated system, a habitable zone planet orbiting a main sequence star passes within half a light year of a central black hole every 2,000 years. During these close approaches, the planet's time rate would slow by nearly 15% relative to the rest of the system. Civilizations rising there might witness stars completing orbits at visibly different speeds during these eras, their celestial clocks literally speeding up and slowing down before their eyes. But the real temporal chaos occurs in the system's gravitational crossroads, regions where multiple stars' time dilation effects overlap. Imagine a spaceship navigating through a zone where three stars' gravity wells intersect. Its bow might experience time passing 5% faster than its stern due to minute differences in gravitational pull across just a few hundred meters. Navigation computers would need to account not just for spatial coordinates, but for temporal ones as well, constantly recalibrating their understanding of simultaneous events across the ship's own structure. What makes these relativistic effects so fascinating isn't just their scale, it's their unpredictability. Unlike the steady time dilation around a single black hole, the ever-shifting orbits of 12 stars create fluctuating pockets of temporal distortion. One year, a particular region might exhibit mild time warping. Centuries later, stellar motions could align to make that same zone a temporal vortex where clocks stutter like a scratched record. Some theorists suggest these systems might even generate time tides, cyclical waves of differential time flow that ripple outward whenever multiple massive stars align, potentially leaving detectable imprints on pulsar signals passing through the area. The ultimate test case: pulsar timing. These cosmic lighthouses normally tick with atomic clock precision, but in duodecuple systems, their pulses arrive scrambled by the system's ever-changing gravity fields. By mapping these distortions, astronomers have reconstructed 4D spacetime maps showing how the star's gravity warps both space and time around them. The results look less like neat Einsteinian curves and more like a crumpled piece of paper. Proof that when it comes to warping reality, 12 stars don't just bend the rules. They rewrite them entirely. Some of the most isolated duodecuple star systems might not be natives of our galaxy at all. They could be cosmic refugees, ejected from their home galaxies during violent collisions or close encounters with supermassive black holes. Astronomers have spotted a handful of these runaway systems streaking through intergalactic space at speeds that defy explanation, untethered to any galactic structure, blazing their own trail through the void. Their composition tells a story of exile, stars with chemical fingerprints matching distant galactic neighborhoods, moving on trajectories that trace back to cosmic-scale gravitational slingshots millions of years ago. One notorious example is System HV 2112, a 12-star cluster barreling through the emptiness between the Milky Way and Andromeda at over 1,000 kilometers per second, fast enough to cross the distance from Earth to the Moon in under 6 minutes. Spectrographic analysis revealed its stars are saturated with elements typically forged in the crowded cores of giant elliptical galaxies, a chemical signature utterly alien to our galactic suburbs. Even more telling, its trajectory points like an arrow back to a violent merger of two galaxies over 2 billion years ago, suggesting it was hurled into the abyss when a supermassive black hole binary went berserk during the collision, flinging entire star systems into the darkness like stones from a catapult. The survival of these exiled systems is a marvel in itself. Galactic ejections typically tear apart stellar groupings through tidal forces, yet these duodecuples cling together against all odds. The secret might lie in their chaotic orbits. Their very instability could be their salvation. As the system was ejected, gravitational turbulence may have locked the stars into an unusually tight configuration, their mutual pulls forming a makeshift gravitational shield against disruption. Some models even suggest the ejection process itself could have triggered temporary gravitational superconductivity, where the star's orbital energies synced in a way that made the entire system behave like a single coherent object, resisting external forces that would have torn a comma group apart. But the real mystery is what happens to these systems in the intergalactic wilderness. Cut off from the fresh gas and dust of a host galaxy, their stars should age in isolation, with no new generations forming to replace them. Yet observations reveal surprising hints of youth, pockets of ionized gas, sporadic bursts of star formation, even rogue planets wandering between stars. The explanation might lie in cannibalism. As massive stars die in these tight quarters, their supernova could shock nearby gas clouds into collapsing, while stellar winds from aging giants recycle material back into slim filaments of star-forming fuel. It's stellar sustainability at its most extreme, a closed-loop ecosystem thriving against impossible odds. The implications rewrite our understanding of galactic ecology. If star systems can survive, even flourish in the void between galaxies, then the universe's habitable real estate might be far vaster than we imagined. Planets in these nomadic systems would face bizarre skies, no galactic arms, no nebulas, just the inky blackness of intergalactic space punctuated by their 12 suns. Auroras might ripple across their atmospheres from particle streams not of a host galaxy, but from the system's own stellar winds bouncing off the thin plasma of intergalactic space. And if life somehow arose there, its view of the cosmos would be unlike anything we know, a perpetual midnight where the only constellations are the ever-shifting patterns of their own captive suns. These galactic orphans challenge the very definition of where a star system belongs. Their existence proves that the universe's gravitational storms can birth survivors tough enough to outlast their origins, carrying the chemistry of distant galaxies into the unknown. Each one is a time capsule and a reminder that in the cosmos, home isn't always a place. Sometimes it's just the stars you're bound to, no matter how far the journey. The idea that gravity itself could be sending cryptic messages sounds like science fiction until you witness the eerie patterns rippling through duodecuple star systems. When 12 massive bodies whirl around one another at relativistic speeds, their collisions and close passes don't just bend space-time, they churn it into a froth of gravitational waves, oscillating across the cosmos at frequencies that, to some researchers, suspiciously resemble structured communication. Take the case of System GR 287, where 3 tightly orbiting neutron stars generate gravitational pulses so precise they form a repeating sequence of peaks and troughs. At first glance, they match simulations of chaotic three-body interactions, but dig deeper and anomalies emerge. The pulses repeat segments in ratios that mirror prime numbers, and subtle harmonics in the waveform align with mathematical constants like pi and the golden ratio. Coincidence, perhaps? But when similar patterns cropped up in 4 other 12-star clusters, a fringe contingent of astrophysicists began asking uncomfortable questions. Could these waveforms be more than cosmic noise? Mainstream science dismisses the notion, attributing the patterns to resonance effects like how a plucked guitar string vibrates at specific frequencies dictated by physics, not intent. In duodecuple systems, gravitational waves bounce between stars in ways that amplify certain harmonics while suppressing others, creating the illusion of deliberate structure. One team demonstrated this by simulating a hypothetical system where 11 stars orbited a central black hole. Without any programmed intelligence, the model spontaneously produced waveforms with Fibonacci-like progressions simply through gravitational feedback loops. Yet the mystery deepens when examining real-world data. Some systems exhibit gravitational bursts timed to intervals that defy orbital mechanics, like the infamous tick-tock sequence observed in system KX9, where waves spike every 17.3 minutes with the precision of a metronome for exactly 11 cycles before going silent. Skeptics argue these are artifacts of overlapping orbits, but supporters counter that no natural model yet explains the abrupt cutoff or the recurring prime-numbered cycle count. Then there's the tantalizing, if controversial, parallel to human technology. The Laser Interferometer Gravitational Wave Observatory LIGO encodes data in gravitational wave modulations when communicating with hypothetical future detectors. The patterns in certain 12-star systems, while vastly more complex, bear uncanny similarities to error-correcting codes used in digital transmissions. Could an advanced civilization be manipulating stellar orbits as a signaling mechanism? Or more provocatively, might gravity itself be a medium for information exchange we've yet to comprehend? The sobering truth is, we lack the tools to definitively rule out or confirm such possibilities. Current gravitational wave detectors are crude compared to the symphony of a duodecuple system. They're like trying to reconstruct a symphony by listening through a cardboard tube. Next-generation arrays capable of mapping waveforms in 3 dimensions may finally untangle whether these patterns are nature's random artistry or something far more extraordinary. Until then, the gravitational chatter of these systems remains one of astrophysics' most tantalizing open cases, a reminder that the universe's loudest signals might be written in ripples we're only beginning to read. Peering into the future of duodecuple star systems is like watching a high-stakes game of celestial Jenga. Remove one unstable piece, and the entire structure could implode or scatter in unpredictable ways. Some of these 12-star monstrosities are cosmic ticking time bombs, their fate sealed by the very gravitational chaos that defines them. While no 2 systems will meet identical ends, astronomers have modeled several terrifyingly plausible outcomes, each more spectacular than the last. Consider the inevitable mergers first. With stars packed so closely, collisions aren't just likely, they're statistically guaranteed. Picture 2 massive blue giants spiraling inward over millennia, their outer atmospheres tangling like gossamer threads before the final cataclysmic embrace. When they finally collide, the resulting fireball could outshine entire galaxies for weeks, forging either an even more massive stellar behemoth or collapsing directly into a black hole. Some simulations suggest these mergers might trigger chain reactions, the sudden mass increase destabilizing neighboring orbits, pulling other stars into the feeding frenzy until half the system has been consumed in a domino effect of stellar cannibalism. Then there's the Great Escape scenario. As stars steal momentum from one another through gravitational slingshots, a few inevitably reach breakneck velocities. In one projection, 3 stars were flung clear of their system within just 500,000 years. one ejected toward the galactic center at nearly 2,000 kilometers per second, fast enough to cross the Milky Way in a cosmic blink. These hypervelocity runaways become interstellar nomads, their trajectories mapping the system's death throes like shrapnel from an explosion. The remaining stars, robbed of balancing momentum, might then collapse inward, triggering a rapid succession of mergers. But the most chilling possibility, total gravitational collapse. If just enough stars converge toward the system's core within a narrow window, their combined mass could exceed the Tolman-Oppenheimer-Volkoff limit, the point where no known force can resist a black hole's birth. Not an ordinary stellar mass hole, but an intermediate monster with hundreds of solar masses. The collapse wouldn't be tidy. As stars plunge toward the event horizon, their tidal disruption would flood the system with enough radiation to sterilize any hypothetical planets light years away. The resulting black hole would then prowl its former territory, feasting on the remaining stars over eons like a spider picking off trapped flies. Yet some systems might cheat annihilation through sheer momentum. In rare cases, the star's chaotic orbits could achieve a perverse equilibrium, constantly stealing and returning energy in an endless gravitational balancing act. These immortal configurations might persist for tens of billions of years, outliving their solitary counterparts by recycling kinetic energy like cosmic perpetual motion machines. Their secret, chaos itself, just as a spinning coin never falls if flicked with perfect rhythm, these stars could theoretically avoid collapse through perfectly timed gravitational nudges, though the slightest perturbation would still spell doom. The wild card in all this, dark matter. If these systems truly harbor invisible halos, as some theories suggest, its gravitational influence could steer their final acts in ways we can't yet predict. Imagine a collapsing system suddenly stabilized by unseen hands, or ejection trajectories bent into captive loops by dark matter's pull. One provocative simulation even suggests dark matter interactions could ignite quasars in systems that should be too small to host them, turning a stellar demolition derby into the universe's most unlikely beacon. Ultimately, these systems remind us that gravity writes no happy endings, only spectacular finales. Whether through fire, ice, or the silent grip of a black hole, every Duodecuple system is born with an expiration date. Their deaths won't be quiet fade-outs, but crescendos visible across the cosmos, brief, brilliant signatures that, in their dying light, might finally reveal the rules governing the universe's most extreme gravitational laboratories. And when the last star falls, whether into the abyss or the void, the echoes of their chaos will linger in space-time itself, ripples in the dark, telling stories of celestial empires that danced too close to the edge. After 30 mind-bending discoveries about Duodecuple star systems, one question towers above them all, a mystery so fundamental it shakes our understanding of cosmic order. Why does the universe permit such gravitational monstrosities to exist? Every law of astrophysics we know suggests these 12-star chaos factories should have torn themselves apart within millions of years. Yet here they persist, some for billions of years, flaunting their impossible stability like cosmic middle fingers to our neat equations. Consider the staggering improbability. Forming one star is delicate enough, a collapsing cloud of gas must fragment just right to ignite fusion. Now multiply that by 12, cram them into a space where some orbits are tighter than Jupiter's moons, and have them survive the gravitational equivalent of a perpetual demolition derby. The numbers are laughable. Simulations show random stellar groupings this size should either collapse into black holes or scatter into the void within cosmic eye blinks. Yet against all odds they endure. This defiance hints at gaps in our understanding so profound they might rewrite physics. Perhaps dark matter's invisible tendrils cradle these systems in gravitational webs we can't yet detect. Or maybe gravity itself behaves differently in extreme multi-body environments, exhibiting emergent properties that only manifest when a dozen massive objects dance in close quarters. Some theorists even speculate about gravitational quasi-particles, where the system's collective motion creates temporary stability, like a murmuration of starlings that behaves as a single superorganism despite being made of individual birds. The implications ripple far beyond stellar mechanics. If nature can sustain such improbable architectures, what else might be possible? Could there be 20 star systems lurking undetected? Might galaxies harbor even more extreme gravitational oddities that make duodecuples look orderly? And most unsettling, if our current laws can't fully explain these systems, what other cosmic phenomena are we misinterpreting because we're missing pieces of the puzzle? What makes this mystery urgent is its potential to unveil new physics. These systems aren't just cosmic curiosities, they're stress tests for general relativity, quantum gravity, and dark matter theories. Every erratic orbit, every survived close pass, even the way light bends through their warped spacetime, each is a clue waiting to crack open a deeper layer of universal law. They challenge us to imagine a cosmos far wilder, far more creative than our textbooks dared suggest. Perhaps the most humbling thought, these stellar anarchies might be the universe's way of showing us how little we truly understand. For all our equations and supercomputers, nature keeps building things that shouldn't exist by our models, not as flukes, but as features. And if the cosmos allows 12 star systems, then the real question isn't how they survive. But what other impossibilities are out there waiting to prove our science incomplete? From gravity-defying dances to phantom stars, time-warping chaos, and signals that tease the boundaries between natural phenomena and something far stranger, duodecuple star systems have taken us on a journey through the universe's most brazen rule breakers. We've witnessed 12 stars doing what astrophysics swore shouldn't be possible, sustaining unstable orbits for eons, birthing planets in stellar hurricanes, hiding black holes in plain sight, and even potentially broadcasting gravitational whispers that defy explanation. These aren't just cosmic quirks, their full-scale revolts against the orderly universe we thought we knew. Take the vampiric stars, siphoning life from their siblings in frenzied feasts that rewrite stellar evolution. Or the zombie suns resurrected from death by gravitational turmoil. Remember the hyper-spinners whirling so fast they stretch into cosmic pancakes, or the magnetic nightmares where field lines knot into luminous nooses between stars. And who could forget the missing mass shadowy anchors of invisible matter warping the system's core, or the rogue stars barging into the chaos uninvited, only to become permanent chaos engineers? Each discovery peels back another layer of cosmic audacity, proving that when it comes to defying expectations, 12 star systems don't just push boundaries, they vaporize them. What makes these systems so transformative isn't just their strangeness, it's how they force us to rethink the fundamentals. Stable orbits, not here, gravity becomes a suggestion. Star formation rules rewritten on the fly, time itself fluid and fractured. Even the fate of planets, life, and the fabric of reality gets tossed into question when you cram a dozen suns into a space where nature's laws seem to short-circuit. These aren't just celestial oddities, they're stress tests for our entire understanding of physics, revealing gaps in our knowledge wider than the systems themselves. So where does that leave us, humbled for starters? Every telescope pointed at these chaotic stellar families uncovers something new, something weirder, something that sends theorists scrambling back to their chalkboards. But also exhilarated, because if the universe can build and sustain these gravitational anarchies, what else might be lurking in the cosmic shadows, waiting to shatter our next set of assumptions? Now it's your turn. Which of these 30 discoveries left you staring at the screen, reeling at the implications? Do you think we're missing a key piece of the puzzle, some hidden law that lets these systems cheat cosmic odds? Or is the chaos itself the point, nature's way of reminding us that the universe thrives on creative disorder? Drop your wildest theories in the comments, because if there's one thing Duodecuple stars teach us, it's that the most thrilling answers often lie just beyond the edge of what we dare to imagine. The cosmos is weirder than we dreamed, and honestly, we're here for it.